So, announcements wise, there's not much. Homework number 2 on chapters 2 and 3 is due on the 17th. That's Wednesday. Homework number 3 on chapter 4 will be due on the 24th. It's a week from Wednesday. So we're continuing on with chapter 4. So, when we talk about motion in 2 dimensions, motion in the x and y dimensions should be solved separately. So we have x equals x naught plus vx naught t plus 1/2 acceleration x t squared. Vx equals vx naught plus acceleration x t, and vx squared equals vx naught squared plus 2 acceleration x times delta x. And then the same thing for y. Y equals y naught plus vy naught t plus 1/2 acceleration in the y direction t squared. Vy equals vy naught plus acceleration y t, and vy squared equals vy naught squared plus 2 times acceleration y times delta y. Okay?
Yeah.
Okay. Just quickly make sure you are marked in. So, for projectile motion, the basic equations are the same as these, with a couple of assumptions. We ignore air resistance. G equals negative 9.80 meters per second. G is 9.80 meters per second squared, and the direction is down. We ignore Earth's rotation. So if the y-axis points up, acceleration in the x direction is 0, and acceleration in the y direction is negative 9.80 meters per second squared. That's the general gist here. So the acceleration is independent of the direction of the velocity. It doesn't matter what direction an object is flying, its acceleration will always be 9.80 meters per second squared downwards. So given that positive y is up, these are the basic equations of projectile motion. It's the normal equations, except acceleration in the x direction is 0, so all of these terms go away. And acceleration in the y direction is minus g. So for all of these terms, is given g, and the minus g minus energy. So these are the equations. And if you write them with delta x and delta y, you can use this chart to figure out which equation to use given what you want to find. So if you're looking for delta y and you know initial velocity and time, then you can use this equation. If you're looking for delta y, you know final velocity and initial velocity, then you can use this equation. Similarly, if you're looking for final velocity and you know initial velocity and time, you can use this equation. But if you're looking for final velocity, and you know initial velocity and delta y, you use this equation. And this is the equation you use for x. In general, for projectile problems, the way you tie x and y together is through time. So here, we have a fish dropped from a crow's nest at the top of the mast of a ship. When the ship is at rest, the fish lands in a bucket directly in front of the mast. If the ship was traveling at a constant velocity and ignoring air resistance, would the fish land in front of, behind, or in the bucket? So when the fish is dropped, the fish and the ship have the same velocity in the x direction. And now these are the equations that describe the motion of the fish. The ship will keep moving at a constant velocity in the x direction, not moving. So the bucket will be moving in a constant velocity in the x direction. And when the fish is dropped, it's immediately above the bucket, so it has the same x position and velocity in the x direction as the bucket. So does anybody think it will land in front of, behind, or in the bucket? So, because the ship and the fish, so as something falls, its horizontal motion doesn't change. So the ship and the fish have the identical horizontal motion. So the bucket will always be directly underneath the fish, and the fish will land in the bucket. Because the velocity in the x direction will remain constant, because it never changes, because there's no acceleration in the x direction. So here we're solving projectile problems. What happens when the launch angle is 0? So when the direction of initial velocity with respect to the horizontal is 0, i.e. when something is being launched horizontally. So this can happen if you're traveling at a constant speed and you drop something, or if you fire something sideways with some speed. But this is something fired or launched horizontally. So in this case, the initial velocity in the y direction is 0, because we're shooting it horizontally. So this would be what would happen if I slid something off the table. You'd be traveling horizontally with some speed. So here are the equations of motion. They simplify even more because initial velocity in the y direction is 0. So x is x naught plus v naught x times t. Vx is v naught x. That's just, this is always the case for projectile motion. And then in the y direction, y is y naught minus 1/2 gt squared. Because again, the initial velocity in the y direction is 0. Vy is minus gt. Vy squared is minus 2g delta y. So here's an example of the trajectory of a projectile that is launched horizontally. Every unit of time, it will travel the same distance horizontally, and it will fall. It will drop down faster and faster, and so it forms a parabola. So here's an example problem. If a person is skateboarding with a constant speed of 1.3 meters per second, so there's your horizontal velocity, and they release a ball from a height of 1.25 meters above the ground, given that x naught is 0 and y naught is 1.25 meters or height h. We want to find x and y at t equals 0.25 seconds and t equals 0.5 seconds. And what are the velocity, speed, and direction of motion of the ball at 0.5 seconds? So I'll let you guys work on that for a few minutes. So remember, I will, for zero launch angle, so these are projectile motion. If the launch angle is 0, v naught y is zero. So let's go over what we know. Person is skateboarding with a constant speed of 1.3 meters, and they release a ball from a height of 1.25 meters above the ground. We know that x naught is 0, y naught is 1.25 meters. We also know that v naught y is 1.3 meters per second. Sorry, v naught x. Misread my own writing. It's v naught x is 1.3 meters per second. V naught y is 0 meters per second because it's being released horizontally. It's just being dropped as you travel along horizontally. X naught is 0 meters. Y naught is height h, which is 1.25 meters. G is 9.81 meters per second squared. That's what your book is using. And t is 0.25 seconds and 0.5 seconds. And we're interested in what x and y are. So we're looking for x and y. We know all the initial conditions and we know the time. So we're going to use this equation for x and this equation for y. Also, we're looking for the speed and direction of motion of the ball at t equals 5 seconds. That's part B, or part C. So first of all, x is x naught plus v naught xt. Y is y naught plus v naught yt minus 1/2 gt squared. In this case, v naught y is 0. So this will go away. Name? Your name? Your name? Sorry. Ephraim. Ah, okay. So that will go away. We also know that our x naught is 0, so that will also go away. So y will simplify to y naught minus 1/2 gt squared. Name? Okay. So if we plug in the numbers, x equals 0 meters plus 1.3 meters per second times 0.25 seconds. Y equals 1.25 meters minus 1/2 times 9.81 meters per second squared times 0.25 seconds squared. So x comes out to 0.325 meters, and y comes out to 0.943 meters. And if we repeat this at 0.5 seconds, x is 0 plus 1.3 meters per second times 0.5 seconds, so it's going to be twice as much. Y is 1.25 meters minus 1/2 times 9.81 meters per second squared times 0.5 seconds squared. So this will be, we will have fallen 4 times as far. So this is 0.65 meters and almost at the ground, 0.0238 meters. And if we want to figure out the velocity, speed, and direction of motion of the ball, velocity in the x direction is just going to be 1.3 meters per second. Velocity in the y direction is the initial velocity in the y direction minus g times t, which is 0 minus 9.81 meters per second times 0.5 seconds, or negative 4.91 meters per second. So those are the x and y components of the velocity. But we want the speed and direction of motion of the ball. So the speed is going to be vx squared plus vy squared, square root. So 1.3 meters per second squared plus negative 4.91 meters per second squared, all square rooted, gives us 5.08 meters per second. And the direction is the inverse tangent of vy over vx, which is the inverse tangent of negative 4.91 meters per second over 1.3 meters per second, which is negative 75.2 degrees. Because this is pointing, it's 75.2 degrees below the horizontal, just about to hit the ground. You know, it's moving downwards quite a bit faster than it's moving horizontally. Any questions about this? This is a pretty straightforward, plug the numbers into the equations and get the answers out. but additionally, it's possible to solve this by as a function of y in terms of x. So if we eliminate t and we solve for y as a function of x, because x, this does assume that x starts at 0, but this is assuming that x equals x naught. But we find that launched from some height, y is height times 1/2 g times x over v naught, because if x equals v naught times t, then t equals x over v naught. And because the initial velocity v naught x is just v naught because the initial velocity is horizontal. And so shuffling some numbers around, we get height minus g over 2 v naught squared times x squared. This is a parabola, and the landing point can be set by finding y equal to 0 and solving for x. And we get, if you fire something horizontally, it will travel from some height h and some velocity v naught. It will travel a distance v naught times square root of 2h over g. And square root of 2h over g is just the time it takes to fall from the height h for something that's drawn. So if you fire something horizontally and drop something at the same time, they will hit the ground at the same time. They fall at the same rate. Any questions about that? So here is a problem using that. So that formula was and that's not 0. Y equals h minus g over 2 v naught squared and x squared and equals, so cannon is fired from the top of a 20-meter high wall. The cannonball leaves the cannon traveling horizontally with a speed of 100 meters per second. So how far from the base of the wall does the cannonball impact? So this is asking that range question. So our initial velocity in the x direction is 100 meters per second. Our initial velocity in the y direction is 0 meters per second. Our initial position in the x direction is 0 meters. Our initial position in the y direction is the height, which is 20 meters. G is 9.81 meters per second squared. Our final position in the y direction is 0. We're looking for our position in x. So x equals x naught plus v naught xt. Y equals y naught minus 1/2 gt squared. Because v naught y is 0. So if we solve for time, we plug in our known y, and we solve for time, we get 0 equals height minus 1/2 gt squared. The time is going to be square root of 2 times height over g. So that's how long it takes for something fired horizontally to hit the ground. So if we plug that time into our x equation, we get x equals x naught plus v naught x times square root of 2 height over g, which is 0 plus 100 meters per second times 2 times 20 meters over 9.81 meters per second squared. We drop the 0, so it's 100 meters per second, or 2 times 20 divided by 9.8, all in the square root, and that's 202 meters. So this is the inside of the square root comes to around 4, a little bit more than 4. So you get about 2.02 times 100, 200. And you could do it directly by plugging it into here. That would just be this last equation. V naught times square root of 2h over g. I just derived it from working out. Because you can always approach this by going, okay, I know a bunch of information about y and I want to find x, so I need time. So find time to go from y to x. That's sort of the general approach for projectile motion problems. You find time to go from y to x or x to y. The time is what connects them. And there are like a few general range equations like this one, and there's another one we'll cover in a little bit for on a level surface fired at some angle. But in general, you find time to figure out what you're going to do. Everybody got this? Okay. So let's move on to a general launch angle. So we did 0 launch angle, general launch angle, v naught x will equal v naught cosine theta, v naught y will equal v naught sine theta. So you get these equations of motion. Now, everywhere we have v naught x, you replace it with v naught times cosine theta. Everywhere we have v naught y, you replace it with v naught times sine theta. Given you have something fired at some velocity at some angle. That's how you find the x and y components. And it gives these equations of motion. So you get a parabolic trajectory. So here's an example. These are snapshots of a trajectory. The red dots are at 0.5 seconds, 1 second, and 1.5 seconds. You go up and down, just like before. Horizontally, you're moving at a constant velocity. Vertically, you slow down. You reach zero velocity in the y direction, and then you speed up in a negative direction on the way down. You get a parabolic path that looks, like that. So, given that, in general, V naught x equals V naught cosine theta, V naught y equals V naught sine theta. Let me see what it is. Yeah. The book isn't consistent in the order. It does the 0 and the y, the 0 and the x. Let me match what I wrote on the other side of the board, which is x0, y0. So if you have a projectile launched from the origin at an initial speed of 20 meters per second at an angle of 35 degrees above the horizontal, we want to find the x and y positions of the projectile at times t equals 5 seconds, 1 second, and 1.5 seconds. So you know the initial speed, you know the initial angle. You can use those to figure out the x and y components, and then plug them into the equations of motion. So this is again a series of fairly straightforward plug into the formula processes with unknown speed and angle. So our initial velocity is 20 meters per second. Our initial angle is 35 degrees above the horizontal. Our initial position in the x direction is 0. Our initial position in the y direction is also 0. That's what the origin is. Launch from the origin tells us. G is 9.81 meters per second squared. And t is 0.5 seconds, 1 second, and 1.5 seconds. And we want to find x and y at each of those times. So x will be x naught plus v naught cosine theta t. So fill that in up here. V naught cosine theta t, v naught cosine theta, v naught squared cosine squared theta. And y will be y naught plus v naught sine theta times t, v naught sine theta, and we have v naught squared sine squared theta. So for part A, x equals 0 plus 20 meters per second times the cosine of 35 degrees. That's 0.5 seconds. Y equals 0 plus 20 meters per second times the sine of 35 degrees times 0.5 seconds minus 1/2 times 9.8 meters per second times 0.5 seconds squared. So x equals 8.91 meters and y equals 4.51 meters. For part B, at 1 second, x, is the, we repeat the formula with 1 second instead of 0.5 seconds. I made a typo. Let me listen. And then this is 1.5 seconds. Was copying the lines above and didn't do a good job transferring. So with 1 second, it's 16.4 meters and 6.57 meters. Make sure those numbers are right. I didn't screw up my math. Nope. And then for 1.5 seconds, we get 24.6 meters and 6.17 meters. So you can see it went up, and then at this point, it's starting to go down. Because at this point, this quantity has overtaken, it's starting to increase faster than the amount of, the rate it falls is faster than the rate it was going up. Any questions about that? So now we can go through and do a similar thing, but instead of looking for the position, we can look at the velocity, speed. So starting values are all the same. We don't know what x and y are. that also I copied this and then didn't change it, so it should be v sub x. And v sub y. I will replace these on Blackboard to fix these typos. After class today. So this is going to be very similar, but instead of using these equations, we'll use these equations. The velocity in the x direction is very simple. It's v naught times cosine theta. It'll be the same for all of them. Velocity in the y direction is v naught times sine theta minus gt. Basically, every second you're going to subtract g from your velocity. So your initial velocity in the x direction is 20 meters per second times the cosine of 35 degrees. That's 16.4 meters per second. That will be the same for all of these. Your velocity in the y direction at 0.5 seconds is 20 meters per second times sine of 35 degrees minus 9.8 times 0.5 seconds, which is 6.57 meters per second. So the velocity as a vector is 16.4 meters per second. X hat was 6.57 meters per second. Y hat. The velocity in the x direction is the same. The y direction, now we subtract 9.81 times 1 second, and we get 1.66 meters per second. We're slowing down. So the final velocity is 16.4 meters per second x hat plus 1.66 meters per second y hat. And for the last one, again, x is the same. Y is 20 meters per second sine of 35 degrees minus 9.81 times 1.5 seconds. So velocity in the y direction is now negative 3.24 meters per second. Once the velocity in the y direction is negative, that means you've passed over the peak and it's on its way back down towards the ground. So the final thing is 16.4 meters per second x minus 3.24 meters per second y. Here we got this. Okay. So here is a problem about actually hitting the ball. So chipping from the rough, a golfer sends the ball over a 3-meter high tree that's 14 meters away. The ball lands at the same level from which it was struck after traveling a horizontal distance of 17.8 meters and hits the green, of course. And the ball leaves the club at 54 degrees above the horizontal and lands on the green 2.24 seconds later. So what was the initial speed of the ball? And how high was the ball when it passed directly over the tree? So here we know things about its motion in the x direction. So finding the initial speed of the ball, we know things about the motion in the x direction and the angle. So we know the distance it traveled horizontally and the time it took to travel that distance. And we know the angle above the horizontal. That will give us, with those, we can find out the velocity in the x direction. With the angle, we can then find out the velocity, the initial velocity. And then once we know the velocity in the x direction, we can find, and the initial velocity, we could figure out what the time it was above the tree is, and then plug in to our equations going forwards to find out what y was at that time. So we know how long it took to get to the dream and how far it was. So we know how fast it was moving horizontally. We know what angle it launched at. Knowing that, we can figure out its initial conditions. And then we can also use that to figure out when it was above the tree and how high it was when it passed over the tree. So as an approach, we know x naught is 0, y naught is 0. We know our initial angle is 54 degrees. We know our final position in x is 17.8 meters, and this is our final position in y is 0. We know the time was 2.24 seconds. We know what g is. We want to find the initial velocity. So here, x equals x naught plus vxt. We can solve for vx by plugging in the known values. So we have 17.8 meters equals 0 meters plus vx times 2.24 seconds. And we find that vx is 17.8 meters divided by 2.24 seconds. The distance traveled over the time it took to travel that distance. So that's 7.95 meters per second. Vx is Vx naught. So we know that equals V naught cosine theta. So we know what theta is. We know what Vx is. We want to find V naught. V naught is Vx divided by cosine theta. So 7.95 meters per second divided by the cosine of 54 degrees gives us an initial velocity of 13.5 meters per second. So that's part A. That's how we find the initial speed of the ball. We find the horizontal velocity. We know the angle. We can then find the initial velocity. Now we know the initial velocity, the angle, and the starting position. So now we want to figure out how high the ball was when it passed directly over the tree. So for part B, we know x naught equals 0, y naught equals 0, x naught, theta naught is 54 degrees, x is 14 meters, g is 19.81 meters per second squared, v naught is 13.5 meters per second, and we want to find y. So we know pretty much everything about x. We know starting position, ending position for x. We want to find y. So to go from x to y, the thing that ties x and y together is time. So we need to know what time is. So our first step will be finding the time. So x equals x naught times v naught cosine t. We want to solve this for t. T will equal x minus x naught delta x over v naught cosine theta. So 14 meters minus 0 over 13.5 meters per second times the cosine of 15.4 degrees, which comes out to 1.76 seconds. So we know that the ball was over the tree at 1.76 seconds. Then we can plug that time in to our equation for y to find out how high it was. Y equals y naught times v naught sine theta t minus 1/2 gt squared. So y equals 0 meters plus 13.5 meters per second times sine of 54 degrees times 1.76 seconds minus 1/2 times 9.81 meters per second squared times 1.76 seconds quantity squared. which comes out to 4.03 meters. So this is a case where we knew about x, and we use that to find time to find y. Commonly, the other common situation you'll run into is you know about y. So you know the starting height and the ending height. And you want to figure out how far something traveled horizontally. So you'll use what you know about y to find out about x, to find out about time, to find out about x. Any questions about this? So here, if a golfer hits a ball from the origin with an initial speed of 15 meters per second at an angle of 62 degrees above the horizontal, and the ball is in the air for 2.58 seconds, and it lands on a green that's above the level where the ball was struck. What's the level of the green? How far has the ball traveled in the horizontal direction when it lands? And what's the ball's y component of velocity just before it lands? I'll let you guys work on that. These are fairly straightforward. So we're hitting the ball from the origin. So x naught and y naught are 0. Our initial angle is 62 degrees above the horizontal. Our initial velocity is 15 meters per second. The time is 2.58 seconds. We're interested in, and g is of course 9.81 meters per second squared. For part A, it's asking for y. Part B is asking for x. And part C is asking for v sub y, velocity in the y direction. So part A, y is y naught plus v naught sine theta t minus 1/2 gt squared. So 0 meters plus 15 meters per second times sine of 62 degrees times 2.58 seconds minus 1/2 times 9.8 meters per second squared times 2.58 seconds squared. That gives you a height of 1.52 meters. X is x naught plus v naught cosine theta t. So x is 0 meters plus 15 meters per second times cosine of 62 degrees times 2.58 seconds, which is 18.2 meters. And then finally, Vy is V naught y sine theta minus gt. So 15 meters per second times sine of 62 degrees minus 9.81 meters per second squared times 2.58 seconds. So our velocity in the y direction is negative 12.1 meters per second. Coming down quite fast. So let's talk about some key characteristics. I'll go over this again next time in all likelihood. We'll see how far we get. We only have like 10 minutes left. So, and I want to go through and actually. So here we have a range equation. If you're on level ground and you fire a projectile at some angle, the distance it will cover is the initial velocity squared over g times the sine of 2 theta. And I'm going to go through and actually show how you get that. So this, the initial and final elevation are the same. So y and y equals y naught. So we start with 0 equals v naught sine theta t. And this needs a clearer minus 1/2 gt squared. We want to find t. So we get v naught sine theta. We want to find t because we're interested in x, and the way you get from y to x is through t. So we get v naught sine theta t equals 1/2 gt squared. We can divide both sides by t. Multiply, which gives us v naught sine theta equals 1/2 gt. Then we can multiply by 2 and divide by g. We get the 2 v naught over g times sine theta equals t. So now we have a formula for t. Now we can plug that into our x formula. We're interested in range, so x naught is 0. So x will be v naught cosine theta t. So we have v naught cosine theta times 2 v naught over g times sine theta. Now we can combine and clean this up a little bit. X is V naught squared over G times 2 cosine theta sine theta. Now, turns out there's a trig identity that 2 cosine theta sine theta is the same as sine of 2 theta. So we use the trig identity, and we get that x equals V naught squared over G times sine of 2 theta. So that's how you derive the range equation. There's some nice things that come out of the range equation. Because this is the sine of 2 theta, it turns out if two angles are complementary, they add up to the same, they add up to 90 degrees. Their range for the same initial velocity will be the same. So if you fire something at 30 degrees at 10 meters per second, and at 60 degrees at 10 meters per second, they'll land in the same place. One will take longer because it'll go higher to travel a further distance than the other, but they will cover the same horizontal distance. So that's how you get this range equation. So x here, this is the range. That's sort of how you go about solving. And that gives you this equation for if you have the same initial and final elevation. Oh. I forgot I had added the derivation when I put together these slides. So I just did that whole thing and I had it on the slides already. So here is the derivation typed out. It'll be on the slides. So this range is maximum when theta is 45 degrees, because the sine of 45 degrees times 2 is the sine of 90 degrees. That's 1. That's the maximum for the range. And so here are the ranges you get at multiple angles. Here you can see when two angles add up to 90 degrees, like 15 and 75, they have the same range, and 30 and 60, and then the maximum's at 45 degrees. And now this is assuming there's no air resistance. In reality, there is air resistance. And when there is air resistance, that favors the lower paths. Just because there's less distance and less time for air resistance to slow you down, basically. So with actual air resistance, your peak distance is going to be at a little bit lower angle. Because basically you get slowed down the entire time. But the calculations for that are horrible and ugly, and so we will not be doing them in this class. Because the air resistance depends on the square of the velocity that you're traveling at, which is just, it turns into some really ugly calculus. So without air resistance, the other nice thing is that we have symmetry. So if you have a projectile at the same height, it will have the same speed, and it will be traveling at the same angle from the horizontal. One will be above and one will be below. So everything is got symmetry. It's going just as fast on the way up as it is on the way down. So this is very useful because often you can break. So often it's and halfway through the time, you'll be at the peak. So often it's helpful if you're interested in like something like, when is the maximum height? What's the maximum height? Well, that's going to happen when your y velocity is 0, so you can use that to figure out the time and then figure out x. that kind of thing. And that's where I'm going to stop for today. We'll go over this again quickly on Wednesday. But have a nice day. I'll see you on Wednesday. Okay.